Okay. Cool. So you missed this stuff on exponentials, but it's just extra, right? Okay. So the second piece here I want to talk about is different types of products. We've talked about matrix product, right? Like just the matrix multiplication. And sort of for standard matrix multiplication, the idea is that you're taking two matrices, you just write them side by side. You don't put like a time symbol or anything between them. And in terms of size, it takes a matrix that's, let's say, like n by k, and maybe b is k by m, I don't know. And then a times b would be n by m, right? So it's like takes the two outermost and the two innermost have to be the same, right? For you to be able to do the matrix multiplication. Is that familiar from, yeah? Cool. So I'm going to introduce two other kinds of multiplication or products of matrices. The first one is called the Kronecker product. So the Kronecker product, it takes two matrices, and we draw like a time symbol with a circle around it to mean Kronecker product of the two matrices. Not related in any way to like direct sums, so keep that in mind. The Kronecker product of two matrices, there's a lot behind it in terms of like vector spaces. You could do the Kronecker product of two vector spaces. We're not going to talk about that. But the Kronecker product of two matrices, maybe I should write out. So it can take two matrices of any size. So maybe the first one is like m by n, and the second one maybe is k by l. Then the result is going to be mk by nl. So like you multiply each of the dimensions together. So I think it's easiest to show this with an example of how this product is like computed. So my example here is if I take the matrix 2, 1, 5, 4, and I Kronecker it with 1, minus 2, 3, minus 4. And in this case, the sizes are the same, but it doesn't matter, right? I just picked two that were small. Do the matrix product here, or the Kronecker product. What you do is you take, so from the first matrix, you look at the first entry, in this case it's 2. You're going to multiply everything in this matrix by 2. And then you're writing that like in the upper left corner, corresponding to where 2 was. So I'll show you. So 2 times 1 is 2. 2 times negative 2 is negative 4. 2 times 3 is 6. 2 times negative 4 is negative 8. Right? So now we're going on to the 1 here. So we're going to do 1 times everything in this matrix. So it'll just be 1 minus 2, 3 minus 4. You see sort of how I'm getting this? So now we're going to do 5 times everything in this matrix. So it's going to be 5 times 1 is 5. 5 times negative 2 is negative 10. 5 times 3 is 15. And 5 times negative 4 is negative 20. And then the last 4 here, 4 times 1 is 4. 4 times negative 2 is negative 8. 4 times 3 is 12. And 4 times negative 4 is negative 16. So that's the Kronecker product. Does that make sense? How like I computed that? Do you have any questions about like, it's hard to like verbalize what you're doing, but like to show you this is what we're doing. You take 2, multiply by all of them, right? You can sort of see how it works. Cool. We'll do an example of it. And then the last thing I want to talk about is another kind of product. It's called the Schur product, S-C-H-U-R. this one's kind of easy to do. It's also relatively simple. It's often called the bad student product because it's what bad students do when they think they're multiplying matrices. So it takes two matrices, A and B. You draw a circle between them to mean sure product. So again, this is not like composition of functions or stuff. It's unrelated to that. The two matrices have to be the same size. They don't have to be square or anything, but they have to be the same size. And it outputs a matrix of the same size. And how it works, I'll give you an example here. You just multiply corresponding entries. So almost like how you would add matrices together. So I've got, my example here is 2, 1, 3, 2, 1, 2, 3, 2, 3, 1, 2, 3. I got ChatGPT to generate me a matrix, and it's not really that nice, but whatever. And if we're sure multiplying it with 2, 1, 2, 4, 3, 1, 3, 1, 3, 1, 4, 2. So I'm doing this multiplication, this sure product. The way it's computed is you just do entry by entry, right? So 2 times 2 is 4, 1 times 4 is 4, 3 times 3 is 9, 2 times 1 is 2, and so on. So 2 times 3 is 6, 3 times 1 is 3, 2 times 4 is 8, 3 times 2 is 6, 1 times 1 is 1, 2 times 3 is 6, and 3 times 2 is 6. Does that make sense, how I did that? It's the bad student product. It's what most linear algebra students think matrix multiplication is going to be, but it's not, right? Is it useful? Yeah, it's very useful. It is useful in a few different ways. So the Kronecker product is very useful. The Kronecker product is used a lot in quantum computing. It's used in machine learning. The Schur product is slightly less useful, but it's useful in a sense that it can help you to compute the Kronecker product. So Kronecker products, like this gives you a giant matrix, right? The Schur product can help you to compute the Kronecker product. So they're connected in that way. And there's other properties. Like I think Schur product is used for some things. I don't really know what it's used for. I think it has some applications in like finance or something like that. I don't fully remember enough about it, but like interest rates or something, I don't remember. I'm not into that stuff, but yeah, hopefully that makes sense. Cool. So I'm going to stop the recording and do some